Okay, so far you have learned to use Runge-Kutta fourth order to actually solve your ordinary differential equations. And just to recap, I will write those equations here. So suppose that we have dy over dt, which is a functionality of t and y. And this was our ODE, or ordinary differential equation. And then what we said was basically this k1, 2k2, 2k3, and k4. And then we said k1 is basically f of tn and yn, and k2 is f of tn, and then we go half a step. And here also we go half a step. This should be k1. And k3, f is tn. We again go half a step. But here it should be k2, half a step. And k4 is also a full step. Sorry for the bad handwriting, actually. Okay, but anyways. So as a recap, we said this collection is Runge-Kutta fourth order for solution of our, let's say, ordinary differential equation. But you can notice that we started with an ODE and finally we ended up with something which is an algebraic equation. So algebraic equation is basically simple multiplications, divisions, and additions and subtractions and so on. So this means we started with an ODE, and in the process of discretization, this word is really important, in the process of discretization, we ended up with a FDE. What is FDE? It is a finite difference equation. And remember also this D here is ordinary differential, but this D here is not differential, it is difference. And the difference comes from that you are dealing with an algebraic equation. Difference. So this was the process of basically going down from an ordinary differential equation, breaking it down, discretize your equation, and then reach to a finite difference equation, and then try to solve it with, I don't know, different methods like Euler, forward, backward, or Runge-Kutta, and so on. But the purpose of this video, I haven't talked about the purpose of this video. The purpose of this video is basically, I even don't want to say many of you, almost all of you have problems with convergence in Runge-Kutta fourth order, and also how you need to deal with it, how you need to put a criteria for this convergence and so on, and how you need to even assess this convergence for Runge-Kutta. I've seen many variations that different groups tried to do, and they were completely lost, I would say. And the purpose of this video is to teach you some important terms, first of all, and among them convergence is one of those important terms. So namely, we are going to talk about, and by the way, I'm going to really briefly talk about these terms, and I will give you a further reading material so that if you are interested, then you can go and grab a book and read in detail, because some of you in the future will actually pick a career which is more aligned with, I don't know, CFD or more of these numerical calculations and so on. So it is good maybe to try to familiarize yourself in the earlier stages with these topics. So the first thing we are going to talk about this terminology, which I said is really, really important, is consistency. Then we're going to talk about stability. Then we're going to talk about order. And at last, I intentionally put this one at last because you bear with me until the end of the video. Okay, at last we're going to talk about the convergence and how you need to assess the convergence in the problem that you have in Aufgabenstellung, right? Okay, but before we start with consistency, I give this a further reading material, further reading. There's a book called Numerical Methods for Engineers and Scientists. It's fellow Hoffman, and probably you will find the version with year 2001. And basically we can check whether the library in KIT has this book or not. Let's type KIT Bibliothek. Okay, it's here. And we're gonna search. Oh, I already searched it here. That's good. So let's... Okay, these are nonsense. Let's make this with... Okay. Okay, the second book in the list, Numerical Methods for Engineers and Scientists by Hoffman in 2001. And you can also see that it is green, so it means ausleihbar. So basically it is available and you can take it from the library in Bibliothek Süd. And also the language is English, bear in mind. Okay, anyways. So if you're interested, you can go in the library and then pick up this book and read more about this stuff. I think it was maybe in chapter 7, if I'm not mistaken. But what is consistency? In simple words, consistency is that you start with an ODE, you discretize, you end up with an FDE, which is finite difference equation. And now if you write, okay, let me make more space. If you write Taylor series for each of the terms in this finite difference equation around the same base point, and I'm hoping that you are familiar with this Taylor series, and if not, let's say immediately we talk about this, it will be the first derivative 1 over 1 factorial and then h, and then the second derivative and then h to the power 2 factorial, and the third derivative h to the power 3. You get the idea, right? Plus other terms. This is going on and on infinitely. And you notice that if you write the Taylor series around the base point, and notice that the base point here is 0, and you can also write 0 everywhere. So the base point is 0 in this case, and if I'm not mistaken, this is specific Taylor series has a specific name also. It is Maclaurin series. But anyways, this is not the point. The point is, if you write the Taylor series for each term in this finite difference equation, you will end up with, because you have first derivative, second derivative, and so on, you will end up with infinite order differential equation. Order. And now if you say, if my h or grid size or a step size or whatever you want to call it goes to 0 in this limit, I will end up with a finite order differential equation. And if this finite order differential equation is identical to original ordinary differential equation that you started with here, you wanted to solve for this, then you will say your FDE is consistent. So this is consistency in a nutshell. I don't want to talk more about this. Just I want to touch on these topics. So this is consistency. What is a stability? So a stability basically deals with bounded and unbounded values. If your FDE, your finite difference equation, tries to generate some bounded values, then you will say I'm dealing with a stable solution. It is in very, very simple words. I am sure that many of you have tried to pick up an H and try with your Runge-Kutta, and then you will see that the temperature is suddenly going up to 10 to the power 30 and so on. So you are generating unbounded results or unbounded solution results, and that basically has two reasons. Either you are making a huge mistake in implementation of Runge-Kutta, or the second reason is that the H that you have picked up for the solution of your equation is in a region that makes Runge-Kutta unstable. And by the way, so Runge-Kutta fourth order is consistent, but Runge-Kutta fourth order is conditionally stable. And what does that mean? It means that you are not allowed to pick any H you like. There is a condition for H. And I don't want to get to this, but to give you a feeling, it's like they start with the solution as a factor of the previous solution, which they call it as the amplification factor. Sorry for the bad handwriting. And then they will say, okay, if I do it for n iterations, then I will end up with y of n g to the power n y of 0. And then they will say in order to have a bounded solution, this value here needs to be smaller or equal to 1. And then this condition will let's say enforce a condition for H. And this condition is different for different finite difference equation methods that you are trying to solve. For Runge-Kutta, it will be different, Runge-Kutta fourth order. But if you see this book here, then you will notice that, yeah, Runge-Kutta fourth order is conditionally stable. And there is a condition for H that you need to pick. Okay, so this is a stability, very, very lightly touched. So what is order? By the way, I forgot to mention that this infinite order differential equation, in the literature, it is also called as the MDE, or the modified differential equation. This is just a hindsight or a side note. But what is the order? Order is basically showing you the rate at which your global error decreases as H goes to 0. So if your grid size goes to 0, you expect that your error should go down, but you don't know with which rate. And that is the subject of the order. How do you calculate it and the details? Again, you need to go and see the book. But basically it is dealing again with Taylor series and so on, and the terms that you are truncating and so forth. But you need to know that Runge-Kutta fourth order has its name fourth order Runge-Kutta because the order of the errors, the global errors, is h to the power 4. But what does it mean? What is the implication of the order? If I know the order of a specific method is 4, 5, or 6, or whatever, what does it mean to me? What it means is that if I solve my equations with h1, let's say h, and I solve my equations again with a value h over 2, which is half of the previous step size, then I can construct an error ratio, which is basically the error in case 1 divided by the error in case 2, which of course the error in case 1 should be bigger, right? Because we are using a bigger step size. And this order-wise, I should write it here, order-wise, it will be such a relationship which will be theoretically 16. So this means if I make my step size half, my error in the solution will be smaller 16 times, theoretically. But normally when you do the calculations, this value is normally higher, and the reason is because those terms which you truncated, they have also, let's say, significance in your solution. Okay, now this is the order. Now we go to the final thing which is important to you guys, and that is convergence. Convergence means if my method, if my finite difference equation is stable and it is consistent, which Runge-Kutta fourth order has both of these, then it will be a convergent FDE. Very simple. But how you need to assess this? Suppose this y bar is my exact solution. If I write my dy over dt, very simple function, I don't know, y plus t and so on, I can integrate this and then have the exact solution of y, which is, let's say in this case, I use the notations of the book so that if later you go and read the book, then you have no issues. But I can calculate this one in this very simple cases by numerical integration, by basically integration, not numerical integration. You can calculate the exact solution of y. But basically in all of the complex engineering and scientific differential equations, this exact solution is not known. So this means this y bar, you don't have it. But you need a mechanism to estimate your error. Otherwise, we cannot say that we are on the right track or not. So how do we deal with this? Let me show it with a graph, very simply. Suppose that this is my Tn, and this is my Tn plus 1. And we start with this point, and I don't know, and then we have here Tn plus half. I don't know, we go here, for example, and yeah, this is the middle point, and then I have this one at this point here, and this is of course the y-axis, and this is the t-axis, and here is the yn, and suppose this guy here is y bar, which is unknown. I don't know it. For most complex problems, I don't know this value. Because if I knew this y bar, I could calculate the error right away. Because the error would be the difference between what I calculate and what I should have, or what I must have as the exact solution. But since I don't have it, suppose now this is like half a step, and then I have, for example, this value here. I show it with a different color. And also note that this here would be in half a step, and the whole thing will be a full step. And suppose that my exact solution at point n plus 1 is basically the value which I calculate or approximate With what? With Runge-Kutta fourth order, or with Euler, or with backward Euler, or with any other method, plus an error term, which I try to show this by, I don't know, such a formulation. If I have, of course, the such an order. Suppose I show my error, the truncation error that I have here, but I don't know this value. And I also don't know this value. And I have one equation and two unknowns, and basically I'm lost. What do I need to do? I do the same calculation, but this time with h over 2. And by the way, I explicitly put here an h, because this is the red one here, because it's going the full step size. I put h here. It doesn't mean that it has, let's say, functionality, but I want to show that this yn plus 1 is calculated with full step size, not with half step size. And now if I do it with half a step size as the black one here, so I go once to here and the second time to here, and there will be a difference between the two. And now I am representing here at this point, I am representing, this again yn plus 1 will be y of n plus 1, which is this time calculated with half a step, plus a, and this time I'm not using h, I'm using h to the 2 to the power m plus 1. But also note that I'm going one step, this will create one of these errors, and I go another step, it will create another one of this error. So this means I need to multiply it by 2, right? Now you see I have yn plus 1 and yn plus 1 here. I can subtract these two equations and then rearrange and solve for my error. So my error was what? Was a h to power m plus 1. And then if I rearrange these, I do the subtraction and rearrange everything, I will end up with yn plus 1, which I calculated with h over 2 step, minus the 1 which I calculated with h step, 2 to the power m divided by 2 to the power m minus 1. So what does it mean? What do I expect you to do? What I expect you to do is basically make such a graph, or make a table. You can also make a table. Basically, let's go here. You can also make a table, have error and have h. You start with, I don't know, h0. You do the calculation, and this is empty. You make your h as h0 over 2, and at the same point, remember, at the same point you need to make the comparisons. You calculate the error here, so this will be E1. You make this one again half, then you calculate E2. And then if you do it for some values, you will see how this error is decreasing. And then you can put a criterion there. You can say that my error, if the absolute value of my error, for example, is below an epsilon, then I can say, for example, if I'm solving dynamically, not in your case, but I can say, yeah, you are free to increase the step size because my error is well below the epsilon criterion. Or if in the case that my error is actually greater than the epsilon, then I say, shush, you need to take care of this, you need to bring down the h because the error is increasing. If you are solving dynamically, of course, in your case I said we are not doing this. But basically you can have a graph or a table to see how these values of the errors are changing as you are decreasing the values of h, or as you are making the h each time divided by 2. Okay, So I tried to make it brief, but I think we are over maybe 20 minutes or so. But I hope that the things that we discussed today will clear these confusion clouds in your mind, and you can come up with a solution in your problem that you are trying to solve.